So what does the inflationary universe scenario tell us? Well, it says the following, that all matter comes from inflation, inflaton. That means we start a universe with nothing except some constant energy density. And the universe grows exponentially many times. And then all the dark energy is converted to ordinary matter. So we have two things gained. We gain space, a lot of space, and we gain all the matter in our universe. So this is what Alan called the outweigh free lunch. It is even possible that the universe is very, very small. That maybe that very small universe come from a quantum fluctuation. Okay? So that means that everything in our universe comes from nothing. What do I mean by nothing? I don't mean vacuum. Vacuum has empty space. By nothing, I mean there's no space, no matter. Okay? And most likely no time. So it's very likely a quantum fluctuation plus inflationary scenario which follow from Einstein equations that everything that we see in this universe comes from nothing. Now, this is a fantastic thing to have if it's correct. And it's amazing that such a scenario makes some very precise predictions. It tells us not only everything comes from nothing, including space. Furthermore, the quantum fluctuation will introduce some fluctuation in the temperature. That means if you look, we say the temperature is 2.725 degrees Kelvin, but if you look at one direction versus another one, they differ a little bit. 1 part in 100,000, probably. Okay. Tiny difference. And they can measure the tiny difference, and we can predict that difference, and that this is essentially the curve. The curve is the prediction, and the data seems to fit the curve very well. So that is, we're doing science. That means you can have a fantastic theory. It's not matter you like it or not, you believe it or not. You tell me what you predict, and then people can go and look and see if you're right or not. And this is not a simple curve. This is called the power spectrum, and essentially a measure of the difference in temperature in 1 part in 100,000. Okay. Different place, different way. And it's amazing the theory and experiment work very well, and the data is improving now. Many experiments or observational experiments are improving this data, and the error bar will decrease very, very rapidly. And then now actually this is not the latest curve, it's the fit to the curve is very, very good. So science is that you make a prediction, and then we do a measurement to see if right or wrong, and in this case, inflationary scenario have very strong support from the data. So this is what happened. This different color is the fluctuation of the tiny little bit of temperature, the density. And that little fluctuation, high density, other thing will move towards it, so there will be instability, and then structures start forming. And then as the universe cools, structure forming, they form stars, collapsing, and then we form galaxies, and that's how our universe today happens. Without that little fluctuation, our universe will still be very smooth by comparison. Okay? So that fluctuation also explains the structure formation. Why we have stars and galaxies and not just having a flat universe, a sort of homogeneous isotropic universe. Sorry about this. Okay, so now we have Big Bang, hot Big Bang, and we say the reason they have hot Big Bang because of inflation. So then we can ask the next question: what causes inflation? Okay. I would say that inflation at this moment have very strong support of data, as we saw, and majority, I'm going to say, I don't know what, maybe by far the majority of cosmologists believe inflation scenario is correct, but still there's some people who want to find alternative, which is very healthy for the field. But we can already ask, if inflation happens, what causes inflation? How does it happen? And that we need to resort to string theory. Okay? And in string theory, what we have is the following. We have atoms, inside the proton neutrons, inside that besides electron quarks. And if you look closely, if we can have a microscope which can look many, many, many order of magnitude closer, we think that according to string theory, that they are made of little strings, tiny little strings. A single string will do, because a string, we know, can vibrate with different modes. So your violin string or guitar string will give you different music. And same thing, different vibration of string will give different particles. One mode will give you the electron, another mode will give you the photon, for example. And furthermore, in string theory, we have another very interesting thing, is that if you have strings, why not have something like membrane, other things? And lo and behold, string theory has brains. As if we call two-dimensional, we call membrane, but then we have three-dimensional, four-dimensional, you just give a name of brains. And string theory also a very peculiar feature. The number of spatial dimensions is not 3 that we live in. It's 9 spatial dimensions. So what happened to the other 6? That's the question we like to ask. And we believe that the other 6 dimensions have been compactified dynamically to very, very, very small sizes. So unless we can look very closely with a big microscope, we're not going to see the other dimensions. But that's what the picture that string theory tells us. So think about a brain, a 3 brain, which spans the 3 spatial dimensions we live in. And inside is all the atoms, molecules, which together form the stars, galaxies. So this is the 3 dimension. I cannot draw 3 dimensions, I draw 2. But this is actually a 3-dimensional space, which is nothing but a brain. We call a 3 brain, 3, 4, 3 dimensional. And inside is everything that we are made of. And then outside, there's 6 other dimensions. But I can't draw 6, so I draw only 1. Okay? So we call outside the brain. And in this case, what we live in a 3 brain. And the size of the 3 brain essentially size our universe. So we live in single 3 brain. This is the picture that naturally suggested by string theory. Okay? The other 6 dimensions are very, very, very small. So we can't see them easily. And this is what we call the brain world. Okay? This is the most natural picture that string theory tells us what our universe really looks like. Of course, at this stage, this is in a speculation part because we don't have experimental evidence for this yet. But if this is true, string theory is the theory that sort of combines Einstein's general relativity together with quantum mechanics in a very consistent way. And it's the only viable model we know that's the case. So physicists and some mathematicians take string theory very seriously. So seriously that they've been working on this for the last 25 years. But if that's brain, then we don't have the one. Maybe we live in this brain, but there's some other brains. Okay? And then this tells us that our universe may be a multiverse, not just our universe. Maybe there's another universe out there where the atom molecules cannot go there. And they have their own kind of atoms, own kind of molecules, maybe. So now, with this picture, we want to say, how does inflation take place in string theory? Well, then it becomes quite easy that we have some brain that is expanding. This is universe expand. This is expanding direction. So this is a 3 brain expanding, and there's another 3 brain expanding. And as they expand, everything on it will be diluted, right? All the matter density go to 0 because they expand a lot. And so they become very flat and totally nothing. The only thing we have is tension, right? You have a brain, you have tension. And the tension provides the dark energy that drives inflation. But they also attract towards each other. As they move towards each other, then inflation takes place. Space being created along this direction. And when they get close enough, they collide. When they collide, they heat up the universe. They produce everything. But since in string theory we have strings, so they produce all sorts of strings. Some are tiny strings, like electron, photon, quarks that we know. Some strings are large, okay, someone may stretch across the horizon, stretch across the universe. And so the universe is heat up. That's the beginning of Big Bang, hot Big Bang. And the important thing is that this scenario one can calculate, looks very good. The key thing is that it produces strings because everything makes strings. Some are small, some are big. The big ones will be what we call cosmic strings. Okay? And some of them can stretch across the whole universe. Some of them can be the size of our galaxies. Some, of course, will be tiny, will be particles that make up you and me. Okay? Each of us is made of billions and billions of tiny little strings, what we call quarks, gluons, electrons. So this is the picture that string theory naturally suggests to us how inflation took place. Okay? And of course, when they cool off, they start from structure formations, stars, galaxies, and what we expect that we see outside our own Earth. So, if spring inflation is correct, it will make one prediction, at least, which is naturally testable. That means it will have a lot of big loops, which we call cosmic strings. It's amazing that the prediction of cosmic strings is completely consistent with all the data we know today. And amazingly, that if the prediction is correct, we should be able to detect that in the next 5-10 years. So that will be a true test. So we call this science because we make very specific predictions that can be tested. And the nice thing is that it can be tested in the foreseeable future, which 5-10 years is a very short time scale in terms of understanding these fundamental properties. So people were searching for cosmic strings in the sky. Now, there are many ways to study the universe. Okay, so it's not just a theory, but also experiments. For example, Hubble telescope, this is taking data very actively now. This is LIGO, gravitational wave detector, with a 4-kilometer arm, one in Washington State, and one in Louisiana State in U.S., and then they have one in Europe, and they're building one in Japan, and they're building one in India. So with these large detectors to detect the waves that come from the gravitational theory that Einstein had. And then in South Pole, there are many experiments. Here I only show a few. Okay? That people really build large detectors to search for different things. You know, a lot of experiments there. And people also in high mountains where the atmosphere is dry, telescope, satellite, many experiments being carried out. So what one said, if we make a prediction, then make sure that somebody can check if you are right or wrong. And that's what we call science. The ultimate test, an idea is correct or not, is the data that people collected from outer space or from the lab. So eternal inflation. While we talk about inflation, there's a possibility where inflation is still happening outside. Okay? Is that true? We don't know. Certainly inflation is not happening here, but it's possibly that at a region we can reach now, inflation is still taking place. That's called eternal inflation. And maybe multiverse. These are questions that we want to ask. So maybe the Big Bang we have is like a single firecracker, okay? Exploded. But maybe that's not quite right. Maybe what's happening is that there's a whole firework show being put on, for example, in festivals, and our universe is just one explosion. Okay? So we have a beginning, but maybe these fireworks have been going on for a long time. So in that sense, that universe may not have a beginning, even though our observable universe seems to have a beginning, because we come from one particular firecracker. We don't know. Okay, these are questions we like to know the answer to. Or maybe what we have is not quite right, that brains will collide, but then they can move away from each other and collide bang many times, and that may be what's happening. We don't know. So now we can come back to, does the universe have a beginning? No. Our observable universe, the part that we can see, surely has a beginning. There's no question about it. But what we can see may be only a tiny part of the whole universe. And if that's the case, then we want to know, does the whole universe have a beginning? Does the multiverse have a beginning? This is a question now we have to be very careful. Okay? If we can never see the other parts of the multiverse of the universe, is this question scientific? By science, we define that you can make some predictions that people can check if it's right or wrong. Okay? If you cannot make such a predictions, or you make predictions that in principle nobody can ever check it, then this is not really science. So maybe this is philosophy. Maybe this is religion. So where's the difference? The difference, I will say, philosophy is something that you have a consistent, logical deduction of what's going to be the case. But there's no way, even in principle, you can think of some experiment to test if you are right or wrong. That's philosophy. Religion is, you don't even have to be self-consistent. Okay, you just have to have faith. And it's amazing is the dividing line between religion, philosophy, and science change over time. What used to be religion, may later on people find a logical way to understand it, or modify it, or evolve it in a way such that its philosophical opinion is there. And what we consider philosophy at some later time, it turns out that we can think about experiments to do to test it. In fact, the scenarios we talk about how the universe began, for ages people have been arguing as a philosophical question. And it's amazing that over time we have been able to convert that to scientific questions. And then people will go and do the experiments, observations to test if it's right or wrong. So the dividing line between religion, philosophy, and science is continuously evolving. And our job as scientists is try to put as much of the philosophical questions to see how we can push them to be scientific questions. And this is what people have been doing in ages. And what's philosophy? People talk about God, no God. And the Bible will say there's an origin to the universe, Genesis, God created the universe, and people argue right or wrong, and now we believe that the universe have a beginning, so somehow it's created. And in fact, how it's created is a little bit more amazing than the Bible tells us, maybe. But of course, Bible can be sort of explained abstractly, or other religion like Buddhism or Muslim. So there's questions we don't know the answer to at this moment, something we do, and yet hopefully maybe we know enough that we can make this more interesting from scientific or philosophical point of view. So what we have learned about nature is that we find that nature can be more amazing than one imagined. I think very few people imagine that the universe, everything comes from nothing. People may think that things pop out created, but now what we find, not only matter, but space is created from nothing. And this seems to be what's happened in our universe. It's amazing that as we understand better about the universe, and actually other scientific questions, more puzzles and questions keep popping up. So you don't have to be afraid that we'll answer all questions. That's not going to be the case. The more you understand something, you can ask a deeper question. You can address a deeper issue. And that actually will for sure be the case in science. And what's more exciting is that not only science is exciting by itself, here I just talked about cosmology, but you can talk about life science, you can talk about many other topics. And a lot of times you ask a pure question out of curiosity, and in answering the question, you will find spin-offs which will transform our society. So I hope that some of you will find science interesting, and you may contribute to society in a way which is unexpected from what we know today. So thanks.